What's up, everybody? Mr. McCarson here with another video. This is continuing our lecture on the history of the atom and atomic structure. This is part 2, discovery of the subatomic particles, where we're going to take you on a journey through the discoveries of the subatomic particles, protons, neutrons, electrons, the nucleus, the electron cloud. We're going to talk about Thomson, Rutherford, Millikan, Chadwick, Bohr, and we'll finish with Heisenberg, and Schrodinger. So thank you for being here and join me on this journey, and let's get started. Now, where we last left off in our previous lecture on History of the Atom, Part 1, we finished talking about Dalton's 5 parts of his atomic theory, which was very influential. It was around the year 1808, and Dalton had basically established from the research of Lavoisier and Humphrey Davy, Joseph Priestley, and many other influential 16 and 1700s age chemists that atoms were the smallest unit of an element, that they were all indistinguishable from one another. So every atom of gold was identical. You could not split the atom apart. Like, atoms were indivisible in the true meaning of atomos all the way back to Democritus, and that they combined in whole number ratios to make compounds like water. So we had established some basic rules, and those rules lasted for almost 100 years. It wasn't until the end of the 1800s, the end of the 19th century, that we had our first major breakthrough with a very famous experiment from English physicist J.J. Thomson. So this is the year 1897. There's a picture of J.J. with his famous cathode ray tube. Now, a cathode ray tube, I'll show you a diagram of this on an upcoming slide, is basically a tube of glass. Think about like a modern light bulb, like the long light bulbs. And in the late 1800s, we had a very important piece of technology created through the Industrial Revolution. We had the vacuum pump. So we were able to suck air out of containers and create what's known as a vacuum, or a lack of atoms in a space. And that was really important to the rise of the technologies that would help us discover the parts of the atom, the subatomics. So it was thanks in part to vacuum pump technology that we were able to create, scientists like Thomson were able to create cathode ray tubes. Okay, and once again, it's a vacuum tube where all the air has been pumped out, so there's no atoms of air. And then what Thomson did was he trickled in a very specific amount of a single elemental gas that he wanted to test. So, like, he would put hydrogen in the tube, or nitrogen, or oxygen, or fluorine, or chlorine. Okay, so he could suck all atoms out of a glass container and pump in a very specific amount of atoms that he wanted. Here's a simple setup for Thomson's cathode ray tube experiment. So this cylinder, this was the glass tube, and what it did is it contained a amount of a specific gas like hydrogen, nitrogen, or oxygen. It had a voltage source, so it was connected to a battery with a wire going to a negative end and another wire connected to a positive end. Okay, and you had metal discs there, so anodes and cathodes. Now, what he was going to do is he was going to run a beam of energy through. He was going to run current through the gas, and when you pass electrical current through a gas, it causes it to give off light. It actually creates what would we think of as a modern day like light bulb. Okay, so he had a beam that went straight across, like you can see in the image here. That beam goes straight through. So what Thomson did to modify his experiment is he took a positive magnet and put it on one side of his cathode ray tube, and a negative magnet and put it on the other side. Now, the space between two oppositely charged magnets is known as an electromagnetic field, and he found that when he would energize the gas in the cathode ray tube, something unique happened, something very specific happened. The beam of light would proceed, and when it went through the electromagnetic field, it would curve always towards the positive magnet. So the beam of energized gas would always bend towards the positive magnet when he made it run through an electromagnetic field. Now, Thomson did this experiment many times and he used a wide variety of different gases. And what he found as he used more and more samples of gas is the beam always bent the same. It always curved towards the positive magnetic side of the cathode ray tube. And what happened is the heavier the gas, the relative weight of the gas, the more it would bend. So, like, oxygen would bend a certain ratio more than hydrogen. Nitrogen would bend a certain ratio more than hydrogen. Fluorine would bend a certain ratio more. So he found that there was a ratio of charge to the mass of the gas, and it was the same with every material. So what he concluded was that there was the same type of piece in every kind of atom. Now, if we think about it, in an atom, and we already kind of know this a little bit in my class, what very famous piece in an atom is negatively charged so that it would be attracted to the positive magnet? So famously, what Thomson discovered in 1897 was the electron. So Thomson had found the electron with his cathode ray tube experiment. Now, he couldn't find the positive for a while. Like, we tried to find a center of positivity in atoms, and Thomson just couldn't come up with an experiment that would allow us to detect a positive region of atoms. So that would come later. But he did come up with a very unique model of the atom. It was one of the first visual models of the atom that tried to depict what was inside of it. He said the atom was like a plum pudding. Now, plum pudding is a British dessert, it's a British food, and it would be very similar to what we know today as like yogurt with fruit in it. So he thought of atoms as a bunch of positive stuff. So think about like strawberry yogurt or cherry yogurt. And the positive stuff was almost like the fluid, or like in a cell, when we think about like cells, it was almost like the cytoplasm or the fluid that filled up the cell. And that there were little fruit chunks that were the electrons, and they were negatively charged, and if you ran electricity through atoms, you could get these electrons to move in and out of an atom. They actually were what was causing the bend in the gases as it ran through a magnetic field. And so, because of this picture, he called it the plum pudding model of the atom, and it was a big hit. This was a very significant step forward from Dalton's atomic theory because it let us know that there were components that were tinier than atoms that were responsible for the properties of atoms. And the first one of significance found was the electron, which is kind of fun to think about because we associate so much of what atoms are with the nucleus and protons that it was unique that in the history of science we found the electron first. And we'll never forget 1897, J.J. Thomson, cathode ray tube experiment. Now, in the history of the atom and the development of our model of the atom, or our various models over the years, there was another major scientist that contributed to our knowledge of electrons, and his name was Robert Millikan. And in 1909, around the year 1909, he had a very famous experimental design known as the oil immersion experiment. And it was based on a similar property as J.J. Thomson's. This is actually a picture of the apparatus that he created. And once again, these early scientists were brilliant to me because they had to construct a lot of this by hand, or they had to go to machine shop workers and have them build highly specific pieces out of a variety of different materials that were available in that era to get the job done. So I always thought that was brilliant. Now, basically, what he did was he had a chamber and he was going to pump droplets of oil into the top of this chamber. Now, the chamber was filled with a fluid, like water like fluid or some type of solution where the oil wouldn't mix with the water. And inside, he had a negative magnetic plate at the top with a small hole through it. The hole was small enough where it would allow particles of oil to move through. On the bottom, he had a magnetic or a positively charged magnetic plate. And what he would do is he would energize and run electrical current through the entire system. And what he found was these droplets of oil would, when it was electrified, when it was energized, these oil drops would migrate through the hole of the negative plate, and they would actually stick to the surface of the positive magnetic plate on the bottom. Now, with some fancy calculations and measurements, what he ascertained from this was he was able to determine that he proved and verified with a different experiment that each electron has a negative charge of -1. And very cool, he determined the mass of an electron. Like, we actually know how many grams an electron weighs, the actual mass of it, and that came from Millikan's experiment. So mass of an electron and prove the charge is -1 with oil immersion was Robert Millikan's contribution to this, to the history of the atom. All right, now this gentleman right here is probably one of my favorite scientists in all of the history of physics and chemistry. This was Ernest Rutherford. So Ernest Rutherford was another English physicist, and he worked. And once again, it was around same thing as, or kind of close to Robert Millikan. It was around like 1908 to 1912. He did a lot of his work in that era. And the first thing I want you to know about Rutherford was he absolutely believed that the plum pudding model of J.J. Thomson was correct. That is how he set up his experimental designs, was trying to learn more and prove more things about Thomson's model. He learned from Thomson. Thomson was one of his mentors. Okay. Now, his initial research question was he wanted to find the outer edges of atoms. He wanted to try and measure the volume or the size of an atom, if you will. Okay. He was a pioneer in the use of radioactivity. So he would become very famous for his discoveries, not just for the brilliant experimental design, but also how he help show the world the ways that radiation can be used to really do some cool things. Now, the type of radiation he used, and we're going to talk a lot about these in the upcoming lessons, is alpha particles. And an alpha particle is a positively charged piece given off by uranium. And think about an alpha particle as simply the nucleus, no electrons, which is why it's positively charged, of a helium 4 atom. So helium 4 is 2 protons and 2 neutrons. So you have a mass of 4 and a charge of +2. And they would shoot out of uranium atoms that were unstable. Think of them as little, like, bullets, positively charged particle bullets that pew, 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 they shot out of a source of uranium like bullets from a gun. Okay. And so that is what alpha particles are. And he would use them to impact other atoms, and he would detect and measure changes. Okay. Now, very famously, he shot alpha particles at gold foil. Why gold foil? Because gold foil can be made only a few atoms thick. It's so malleable that you can press gold foil so thin that we can measure its thickness in hundreds to thousands of atoms. So very, very thin foil. So Rutherford's famous experiment was known as the gold foil experiment because of the thin gold foil we just talked about him using. And what he was trying to do was shoot the alpha particles at gold foil, and around the gold foil he had a fluorescent screen, and fluorescent screens would glow and show you where the alpha particles hit upon impact because of the transfer of energy. And so here's what his famous gold foil experiment looked like in a diagram. So in Rutherford's gold foil experiment, he started off with a lead block because you had to protect from the radiation of uranium and direct it. And lead is one of the greatest natural sources we knew of very early on that blocked radioactive particles. And then inside, he had a piece of lead that was kind of shaped like the barrel of a gun. And then he had a source of radioactive uranium. And what would happen is the alpha particles would shoot out at a very fast rate, very tiny. And remember, little positively charged bullets with a charge of +2 and a mass of 4. and he had gold foil, very thin gold foil right in the middle, and then he had a fluorescent detection screen going around the gold foil to detect where the alpha particles hit when they struck the gold foil. So this was the basic setup. Now, here's what Rutherford expected. He expected the particles of alpha to pass through without changing direction very much because the positive charges in the plum pudding model, remember he believed plum pudding, the positive charges were so spread out that there was essentially nothing for the positive alpha to deflect or rebound off of. Remember, if you're a positive particle, you're attracted to negative, but you repel or you bounce off of other particles. So if you have an alpha coming this way and there's a really strong positive area, you should deflect or you should bounce back and repel off of another positive. Now, he didn't think this was going to happen because of the plum pudding model that J.J. Thomson developed, okay? But what he would find would change the world. So here's what Thomson expected. He expected, I hope you like my pew sound effects, he expected that almost 100% of the particles would blast straight through the gold foil because there's no strong positive force in atoms in the plum pudding model to stop the alphas, right? It's like imagine shooting or playing handball or basketball and there's no backboard, right? If you shoot a basketball and you miss the hoop and there's no backboard, there's no rebound because there's nothing to stop or bounce the basketball off of. So he thought that 100% of the alpha particles would go straight through the gold foil. That's what he expected. On a small scale, here's what it looked like. So here's our plum pudding atoms. And because there's no like really strong positive region in the plum pudding model of the atom, it's all spread out. He thought that the alpha particles would just shoot straight through. So all of these beams are alphas that I tried to animate, and they shot straight through. There's nothing for them to repel off of. Okay, and famously, here's what he got. So first off, pew! There's a vast majority of the alpha particles did go straight through. So he expected like 100% to go straight through, and it was still quite a lot, like 90-ish% went straight through. So that was pretty expected, but here's where it started to get weird. He started to get pew, pew, pew deflections. So he started to get some particles that instead of going straight, started to bend and hit the indicator at angles. And then it got weirder because he detected a very few particles coming down at extreme angles, and this is what really was the mind bender. This changed everything. This changed Thomson and made Thomson's model no longer viable. He got rebounds. What the heck? Alpha particles in a very tiny amount of them, not a lot, but he did detect alpha particles bouncing almost straight backwards. They were hitting something and being thrown back and repelled. And this was really groundbreaking. This was not expected. And once again, that's kind of a big deal in the history of science. A lot of the most incredible discoveries we've ever had were not what we were trying to figure out, okay? Now, let's talk about what he discovered from these revelations in his data. So, what did Rutherford's data in the gold foil experiment lead him to conclude? Still, and this still was like part of Thomson, so Thomson wasn't completely destroyed, he found that the atom is mostly empty space. And that still holds today. You and I, ladies and gentlemen, and the table that I'm sitting at in the chair that I'm sitting on are mostly empty space. Okay, don't take it personal. However, he found a small, dense, very heavy positive piece at the center of all atoms, and he called it the, drumroll, the nucleus. So Rutherford discovered the nucleus. Okay. Now, what he found is the alpha particles, as they shot through, if they got close enough to the nucleus, because they're both positive, that would cause them to rebound or deflect at angles. If the alpha particle was far enough away, the alpha particle would still pass straight through and was unaffected by the nuclei. Why? Because nuclei are small. Remember, a marble on the pitching mound of Dodger Stadium, if the outside of the stadium was the electron cloud, the marble would be the right scale for the size of, for example, a single hydrogen proton nuclei in a hydrogen atom. Here's what it looks like with a little animation. So you can see the vast majority of particles pass straight through, but if you get close enough, you will deflect. And how close you get to hitting a nuclei causes extreme deflection. In a very rare circumstances, you hit a nucleus directly with an alpha particle, it will bounce straight backwards. Okay, so that was the revelation that Rutherford's gold foil experiment is so famous for, and why Rutherford is a really, really influential scientist in the 21st century and the 20th century. He's still changed everything with this discovery. So here's a picture of the updated Rutherford model, which is different than plum pudding. So Rutherford found that the atom is composed of small, dense, positively charged core called the nucleus. Now, he knew the nucleus was positive, but he didn't know about protons or neutrons yet. That would come later, okay? He still felt that electrons were moving around the nucleus and they were negatively charged, and that balanced neutral atoms. And he found that the majority of electrons were in a space that was very empty. He knew electrons didn't have a lot of mass and that the nucleus had the vast majority of the mass, and he felt like they went and moved around and that the electrons were related to energy of the atoms, which we could still attribute back to Thomson's experiment. So this is a diagram of what we call the Rutherford model. Now, Rutherford would go on to make significant discoveries in other areas, but he made one more major discovery in the year 1917. He was doing a modified experiment with alpha particles where instead of shooting them at gold foil, he shot them in a tube that contained atmosphere, so just the air that we breathe. And that's the majority of which is the element nitrogen. It's 78% of the atmosphere. And what he found is when he shot alpha particles through the atmosphere, he actually detected the creation of hydrogen atoms. So he started to kind of do the math and figure out, okay, what's going on if I'm shooting alpha at nitrogen, and what he was creating is an atom of oxygen and an atom of hydrogen. What he found was that the nuclei of a hydrogen 1 atom was actually a component that was being stacked together to build larger nuclei of things like nitrogen and oxygen atoms, and he came up with a term for these. He called these pieces protons. So Rutherford in 1917 went further on to discover with this experiment protons. Here's a basic design of Rutherford's apparatus for discovering protons. Once again, he had a battery source to generate an electrical current. He would take alpha and he would shoot alpha through this cathode ray tube through the atmosphere, and he had detectors that would actually measure the different atoms created, and he was detecting hydrogen when he shot alpha at nitrogen, and that led him to believe that he was knocking off individual protons from the nucleus of nitrogen when the alpha fused with that nucleus to become helium, right? So if there's 2 protons in helium and nitrogen has 7, when helium hit the nucleus, when the alpha hit the nucleus of nitrogen, it was adding 1 proton to the nucleus of nitrogen to make an oxygen atom, but 1 proton was shooting off, and that's what he was detecting as hydrogen. Okay, and so that's what led him to conclude that protons were the building blocks of the nucleus of an atom. All right, now we're moving forward, and here's a picture that many of you in my class are already familiar with. We've been building these, but let's talk about the history of the scientists that came up with this very famous ring model of the atom known as the Bohr model. And Bohr model is named after Niels Bohr, who was a Danish physicist that actually was a student of Rutherford's, okay? And what he proposed was when he actually played with Rutherford's basic experiments, he started to understand that not only did electrons move around the nucleus, but they had very defined energy levels, right? And he postulated that these electrons had rules that they had to follow in terms of how far away a certain number of electrons could be from a nucleus. He called these energy level shells or orbitals, and he felt that electrons orbited the nucleus of an atom kind of the way that the planets orbit the sun, right? And he actually went further to show that when you add energy or take it away from an atom, you can actually get electrons to jump between the rings. And you guys will learn more about this and see it demonstrated when we show what's called the flame test, right? We'll talk about the electromagnetic movement and the release of photons of light as electrons boost to a higher energy state and then fall back to the ground level. That's all related to Bohr's research and the ring model of the atom that Bohr developed. Now, this model is very famous and it's often the beginning teaching tool that we use to help young chemists start to learn the basic rules that electrons operate by, but it is overly simplistic because it assumes that electrons move in a nice geometric pattern, which is not the truth that would arise later. This model lasted from the early 1920s. However, by the 1930s, we had actually moved on to quantum mechanics. And the big problem with the Bohr model is it works really well for small atoms, hydrogen, helium, lithium, beryllium. But as soon as you move down the periodic table, the rules of the Bohr model start to fall apart and get very weird. So it is a very good visual tool. It's like riding a bike with training wheels, but eventually we have to take those training wheels off and transition into what we know as the quantum mechanical model of the atom, which is still the working model today that has been uh, verified countless times in the last 100 years. Now, we'll kind of take a quick detour here because we need to discuss how the third subatomic particle was discovered. Neutrons weren't discovered until 1932. So we had the Bohr model, the Rutherford model. We had been knowing about electrons for 30 years with J.J. Thomson, but it was an experiment by an English scientist, James Chadwick, in 1932. And what he did was a really cool setup. So same thing, alpha particles. This time he didn't use uranium, he was using polonium. But he shot positively charged alpha particles out of a polonium source. And he shot it at a really thin sheet of beryllium, which is a metal between lithium and boron, a very, very thin metal. And when he shot alpha at beryllium, there was a mysterious particle that was getting knocked off. And what he did is, after the beryllium, he had a layer of thin parafilm wax. And parafilm wax is really rich in hydrogen atoms and carbon atoms. And what happens is there was this mysterious piece that was being broken off of beryllium, but it wasn't alpha. He knew it wasn't alpha. And this piece would travel and hit paraffin. And when it hit the paraffin, it would cause hydrogen protons to break off and shoot, and he could detect that with a Geiger counter, which measured different types of radioactive particles. Okay, and by the way, Hans Geiger was a lab assistant to Rutherford. So when we talk about Geiger counters, Geiger worked for Rutherford. Once again, a lot of this goes back to Rutherford. Okay, now he knew that this mysterious piece had a mass of 1, but it didn't have a charge. When he started to look at the nuclear mechanics, he realized it had to have a mass of 1, but because of the interactions, it was neither positive or negative, it was neutral. And so he would go on to later call this piece the neutron. He had discovered the neutron in 19 1932. That was James Chadwick. All right, now, the rise of quantum mechanics. So there were two very influential scientists, and many people worked on quantum mechanics. Many of them were students of Bohr that saw the issue with Bohr's model of electrons moving in ellipses, in an elliptical pattern or a perfect circle. The main person is this gentleman pictured in the top here. This is Erwin Schrodinger. Erwin Schrodinger. And Schrodinger was very famous because in 1926 he discovered the mathematical formula for the truth of how electrons move in an atom and in the universe. Electrons don't move in a straight line, and they definitely don't move in a circle or elliptical pattern. Electrons are waves. And they're not just one wave, they're actually two waves that simultaneously move together. We call it the dual wave function of electrons. It is one of the most famous equations ever derived, and this equation is the fundamental basis for quantum mechanics. Where Bohr got it wrong is he thought of electrons as little bullets. Electrons are not little bullets. They're not little balls that move around a nuclei in a very geometrically simple pattern. They are actually waves of energy, and those waves move in a wave-like pattern around the nucleus. Okay, so Schrodinger really was the pilot and the person that kicked off quantum mechanics. Okay, now because of this, Schrodinger proposed that there were two regions to the atom. You still had the nucleus, which was protons and neutrons. Very, very heavy, very dense, very positively charged, but very insignificant, very tiny volume of the overall atom. And then he found that electrons were in a region that he called the electron cloud. And instead of rings, what he proposed is electrons occupied very weird shaped orbitals that were properties of energy and distance and possibility of finding a wave like electron. And he felt that electrons moved around and they like to pair up. They like to entangle. So, like two electrons would like to occupy one orbital, they would spin opposite directions, and they had a probability of being found in these different clouds. And oh, by the way, it gets more complicated because those clouds overlap other clouds. So it becomes largely more complicated in the quantum mechanical model than good old Bohr. Okay, and we'll talk about this person next. This is Heisenberg. All right, so this gives me nightmares of going back to calculus in college. But we are not going to be using in our high school chemistry Schrodinger's equation for the wave function of an electron. But here it is. If you want to see some early calculus, here you go. You can take this to Mr. Conway or Mr. Coots and have fun with it. Have fun with it. So basically, you have the square root of -1 multiplied by Planck's constant, and then you have derivative of the rate of change with respect to time multiplied by this is Schrodinger's quantum wave function. It's a constant. And on this side, that's equal to the Hamiltonian operator multiplied by that quantum wave function again. Good luck. Come back, take me to lunch in 6 years, and please explain this to me all over again, because that gives me nightmares of 25 years ago in college for my calculus classes. But anyways, if you're interested, there is Schrodinger's equation. And in a nutshell, for people like Mr. M, that this math is a little beyond him in his old age. In 1926, he used this to mathematically. This equation was used to prove that electrons function as dual waves and not small solid particles, right? And they had the probability to exist in specific regions around a nucleus that he called orbitals. Now, he concluded these orbitals had unique shapes, energies, and rules which governed how wave-like electrons behave in them. Now, we will learn that. We're not going to work with the math, because even Mr. M's not quite in his prime in calculus anymore, and many of you guys are a year or two away from taking that with Mr. Conway. But in any case, we will talk about the rules of quantum mechanics, what we know as electron configuration rules. And this famous equation really gave rise to our quantum mechanical model, which we're going to dabble our toes in and start to try to visualize and wrap our heads around. But if you're going to go really deep down the rabbit hole of chemistry and engineering and physics, you're going to mathematically work with this at much higher levels of calculus later on in your career. My goal is just to kind of show you what's coming next. Now, before we get into any Breaking Bad comments, no, like Heisenberg, it's not Heisenberg from Breaking Bad. Yes, I've seen Breaking Bad. Great show, great actors, interesting ideas, but no, that's not the high. This is the real Heisenberg. So Heisenberg's uncertainty principle is a really cool concept in quantum mechanics that's very mind bending and trippy. Um, he developed it in 1927, and his name was Werner Heisenberg, and he was a German physicist. And he very famously worked with Schrodinger's equation, and he came up with this uncertainty principle, which says something wild. Said that because electrons are a dual wave function, what he mathematically derived is that it is impossible to know both the location and the speed or momentum of an electron wave at the same time. In fact, what he said was kind of a paradox. The more accurately, or the more confident you are about the position of an electron, the less you know about its speed and momentum. The more confident you are about the speed and momentum that you measure of an electron, the less likely you are to put your finger on it. So it's like if you can put your finger on an electron and locate it, you can't tell its speed or momentum. If you can measure the speed and momentum, you can't put your finger on the electron. Mind-blowing stuff. But that gets into fun things like quantum entanglement, other wild stuff we'll talk about with orbitals, and why this is really why Bohr was incorrect. Is Bohr basically gives us the image, and it's not true, but it's basically like you can put your finger on an electron in the Bohr model. That ain't reality. That's not the reality of how electrons work in an atom. It's much more fuzzy, if you will, and that's what both Schrodinger with his wave function of an electron equation and Heisenberg's uncertainty principle equation brought to quantum mechanics. Okay, and we're gonna see more images of what quantum mechanic atoms look like in the orbitals s, p, d, and f in an upcoming unit on electrons and light. So, anyways, let's go ahead and finish. And I really feel this is a beautiful diagram to illustrate the different models that we went through from Dalton to Schrodinger. So we've got John Dalton here in the early 1800s, where atoms are basically just small spheres. There's nothing that makes them up. They're indivisible. They're not different from one another. There's no isotopes, protons, neutrons, electron clouds, nuclei. None of that occurred. Then we have Thomson's plum pudding model, late 1800s, early 1900s, very famous for showing that there are pieces that are smaller than the atom that have unique properties that make up the atom, specifically the electron. Then we get to Rutherford, who I believe really was the tipping point in this story of the history of our atomic models. And in 1911, his discovery of the nucleus really set the course for then Niels Bohr to come modify that with his Bohr model or ring model, which we still do in class today with breakfast cereal. It's a great teaching tool. And then finally, that led to Schrodinger with his wave function equation of electrons and Heisenberg's uncertainty principle. With what we kind of visualize today, or what we know today, is in this model in atomic theory, this is the model that is the most correct based on all the research evidence we've had. This does allow us to predict the behavior of matter in ways that are consistent, and we really have not found anything better than quantum mechanics at this point, even to the point of frustration of Einstein, because Einstein didn't like some of the things that quantum mechanical model predicts, like quantum entanglement of electrons and what he called spooky action, which we'll talk about in a special video. But it hasn't been wrong yet. The math of Schrodinger and Heisenberg and all the other great minds that helped develop quantum mechanics, it's still working today, and we have all the cool things we have in technology, medicine, industry, the rad things that make humans the technological beasts we are today is because of quantum mechanics and the physicists and chemists that laid the groundwork for it. So I hope you enjoyed this journey. We're now going to move on in part 3 to isotopes and how to count subatomic particles correctly and write isotope symbols and notation. But if you enjoyed this video, please give it a thumbs up. Don't forget to subscribe. And as always, take care, have a good day, and don't stop studying your chemistry. We'll see you on the next one. Bye.